Hello again, my dear students, and welcome to our third chapter in the Semiconductor Devices course. In the previous chapter, we have introduced together the first foundational electronic devices, semiconductor electronic devices, which is the p-n junction. In the next chapter, we are going to tackle the most famous semiconductor devices, which is the MOSFET with the metal oxide semiconductor field effect resistor. Here in this lecture, we are implementing some sort of bridging between the p-n junction and the MOSFET. We are going to consider what's called the metal semiconductor junctions, which is one step toward the metal oxide semiconductor junctions or field effect resistors. We are going to tackle three main types of junctions. The first two are a metal semiconductor junction under the name Shockley barrier diodes and ohmic contact. And the third is still a semiconductor junction like the one we have already studied in the p-n junction, but in this time it's called what's called heterojunction. I mean that we are combining two different materials to form a semiconductor junction. So now please accept my invitation to start sharing my presentation slides and to start together the journey for the semiconductor metal or the metal semiconductor junction. Okay, let's now start together this lecture dealing with metal semiconductor junctions. Okay, so in the previous lecture, my dear students, we have already investigated together the p-n junction. And the concept of implementing or sketching the energy band diagram for a p-n junction is simply we have originally two different doped regions. We have a p doped region and we have a p-n and n doped region. Whenever we are going to merge these two regions together, then we are going to start with a thermodynamic equilibrium condition where the total current flowing in this device is equal to 0. And in this stage, you have a constant Fermi level, as you can see here. And then you are going to merge these two semiconductor parts based on this horizontally aligned Fermi level. Accordingly, the building potential or the barrier starts to appear and all these stuff related to p-n junction, where we have already investigated a complete lecture in lecture number 2 of this. Now, what we are going to do is we are going to repeat the same process, but instead of having two semiconductor material, we will have one semiconductor, maybe n doped or p doped, whatever, and we have a metal. Herein, we have first to investigate how we can plot or sketch the energy band diagram for a metal. Because usually in our materials, as well as in our semiconductor devices modules, we have dealt with a semiconductor energy band diagram consisting of a conduction band, valency band, Fermi level, blah, blah, blah. But we have never dealt with a metal energy band diagram. So first, we have to introduce together how we can plot the metal energy band diagram. As you know, maybe you can remember this from our revision chapter number 1. As you know, we don't have what's called a energy gap in the metal. If you remember this slide where we plot the difference between the energy band gap for a semiconductor, conductor, and insulator, and I told you that for the insulator we have a very large band gap, so that whenever or whatever energy you have, you will never be able to create free electrons. And in the semiconductor, you have an energy band gap that can be tackled, can be paused whenever you have internal or external sources of energy. But for the metal, we already don't have an energy band gap. Electrons can move freely from the valence band to the conduction. So this is the first observation, that in the metal, we don't have a conduction band and a valence band. But as far as this metal obeys the very basic thermodynamic equilibrium condition, then it should have what's called a Fermi level. And herein we will call it EFM, or the Fermi level for the metal. So we have EFS, which is the Fermi level for a semiconductor, and EFM, which is the Fermi level for the metal. But as you surely remember, in energy band diagram, we don't have what's called an absolute energy. So you will never see that I told you that the Fermi level has an energy of 25 electron volts. This is impossible. We usually have what's called the relative energy. So I told you, for example, that the distance between the conduction band and the valency band is blah, 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 which is the energy gap. So for example, in silicon, the distance between the conduction band and the valency band is 1.12 electron volt. Okay, if the material is n-doped like this material, then the conduction band and the Fermi level are close. So the distance between them is somehow small with respect to the distance between the Fermi level and the valency band. So this is what we usually do, is to compare or to refer to the difference between two energy levels. So in order to make the same in the metal, we have to have a reference. We don't have in the metal a conduction band or a valency band. So we should have a reference to refer to the Fermi level with respect to it. Our reference, my dear students, is what's called the affinity level. By definition, the affinity level is the most far level in the material with respect to the nucleus. So if you remember, we have what's called the valency band, which is a partially filled band. And then we have what's called the conduction band, which is theoretically at 0 Kelvin is an empty band. And this spherical band is a series of combined energy levels. And then, of course, there is an end. There is a point at which, if you give the material energy greater than, the electron will be removed outside the material itself. Not transfer from the valence band to the conduction band, but it will leave the material. So this level is called the affinity level. So the affinity level is the most far level in the material with respect to the nucleus. And of course, it can be defined either in the metals or in the semiconductor because it's something generic. Any material has an affinity level. Accordingly, we will going to make this affinity level as our reference. And herein we will define what's called the work function or the phi. The work function is the distance between the affinity level and the Fermi level. So for semiconductors, we are going to call it phi s, or the semiconductor work function, as the distance between the affinity level and the Fermi level of the semiconductor. And for the metals, we are going to call it phi m, or the work function for metals, where it is the distance between the affinity level and the Fermi level for a metal. So the given for this example is, we have two givens. This is very important medicine in this lecture. So whenever you start a metal semiconductor junction, you have to ask yourselves two questions. And based on these two questions, you will get the answer. The first question is, what is the type of the doping for the semiconductor side? So of course, in this case, we have an n-type semiconductor material because the Fermi level is closer to the conduction. The second question is, what is the relation between phi m and phi s? And it's quite observed that phi m is much greater than phi s in this case. So the givens here is semiconductor is n-type and phi m is greater than phi s. What is required from your side is to plot the energy band diagram to merge these two devices. Herein, we are going to do the same steps we have already done in the PM junction. As far as the semiconductor matter is under thermodynamic equilibrium, then the Fermi level should be horizontally aligned. Then let's go together and see how we can combine these two levels together to form a combined energy band. Now I'm going to use my white paper and start plotting. Okay, so let's first start with the graph we already have plot, or we have already have shown in the slide. So As you can see here, this is the affinity level for the semiconductor. And we have a conduction band, a Fermi level, and a valency band. So this is EC, and this is EFS, and this is EV. And as we mentioned, this distance is phi s, or the semiconductor work force. So this is what about the semiconductor side. What about the metal side? Again, we have a film affinity level, and we have here somehow here, for example, we have EFM, or the Fermi level for a metal, and now we have this is phi. So as I mentioned, we have two givens in this problem. The first given is that the material is an n-type semiconductor material, and the second given is that phi m, as we can see, phi m is greater than phi s. Okay, now what we are going to do, my dear students, is we are going to plot an energy band diagram for this semiconductor metal junction under thermodynamic equilibrium. Perfect. So as far as this semiconductor is under a semiconductor metal junction is under thermodynamic equilibrium, then that means that we have an horizontally aligned Fermi level. So we will start with this line, which is the Fermi level, and then we are going to plot everything with respect to this line. So what we are going simply to do, my dear student, is we have here a conduction band and here a valency band. And then this should be banded like this here and here. So this is the Fermi level. As you can see, it's aligned, and this is a metal semiconductor barrier. So we are just merging this together. So whenever you merge this together, you will find this alignment, as you can see. Okay, so now we are going to ask ourselves a very important question. Is okay, is this junction will lead to the motion of the majority carrier, or it will block the majority carrier? Of course, whenever I'm talking about majority carriers, I'm talking about the semiconductor side, because in metals there is no majority or minority. The majority and minority is defined usually in the semiconductor side. So if this material will going, so is this junction will going to drift carriers, or it will going to block carriers? It's very easy. So we have here majority of electrons, because this is an n-type. Now, can electron move from the semiconductor side to the metal side? Surely the answer is no, because whenever the electrons try to move, it will be obstacled by this barrier. This barrier will prevent electrons from moving from the right hand side to the left hand side. So generally speaking, electrons will not be able to move in this condition. Okay, perfect. So herein there is a barrier that prevents majority carrier from moving from this side to this side. We can actually calculate the height of this barrier, because simply what happens is you now want to make this EFM and EFS to make them aligned. So simply what you did is like you shift this graph, this energy band diagram, downwards so that you can horizontally align EFM with EFS. Just if you can move this downward so that EFM and EFS become a continuous line. So how much energy you will push this downward to make them align? This is very simple. This is different, which is phi m minus phi s. So this height is equals to phi m minus phi s. So you have this height. This height is the height of the barrier that prevents your electrons from moving from the semiconductor junction to the metal junction. And accordingly, you don't have a flow of current due to the semiconductor side. This is typically what we have in this device. If you have a good memory, you will remember that this is typically like a p-n junction. A p-n junction under thermodynamic equilibrium, if you remember, my dear students, no majority carrier can move because majority carrier see some sort of a barrier, which is the building potential, and so majority carrier are not be able to move. And in order to make this carrier, in order to push these majority carriers to move, what we did is we connect the p-n junction with an external voltage which has a polarity against the building potential and greater than V naught, if you remember. And in this case, this this barrier turns to be a drift. So what we can do here is typically the same. Let's return back to our slides again. So this is the p-n, the metal semiconductor junction. Now we pull this downward. We shift this downward with a distance phi m minus phi s in order to make this horizontally aligned. And then what we did is that we have this barrier, and this barrier will prevent the majority carriers, which is electron in the semiconductor material, to move to the metal. So we don't have a motion due to a majority carrier. Our motion will be limited to the minority carriers, which is holes, of course. So this is the case, as you can see in this semiconductor metal interface. What if we apply a voltage? Then we have two options, my dear students. The first option is to apply a forward voltage. What I mean by forward voltage is that this voltage is against the built-in potential, as we did in the p-n junction. So this barrier will start to decrease, as you can see here, which is V naught minus V. V is the applied voltage, and V naught is the built-in potential, which is phi m minus phi s. So this is what we can do here, that we apply a voltage, and this voltage decrease the barrier. And whenever we have V forward greater than V naught, then this barrier will turn to this drift, and you will have a characteristics similarly like the p-n junction. On the other hand, you can apply a voltage which is in the same polarity like the building potential. So you increase the barrier, and this is the reverse condition or the reverse characteristics for the IV curve for this. So it's typically like the p-n junction, but there is an only difference, my dear students, between this junction and the p-n junction. The difference is the type of the carriers. In the p-n junction, my dear students, if we return here, yes, sorry. Okay. Whenever you have a forward voltage, you will have a current due to electrons and due to holes. So p-n junctions are what we can call a bidirectional or a bipolar junction. A bipolar junction means that these junctions creates an electrical current due to the motion of electrons and as well as due to the motion of holes. However, in this case, whenever you have a forward voltage, your current will be mainly due to electrons. Of course, you will have holes, current, but due to the majority of the electrons and the minority of holes, you can easily neglect the Hall effect, and you can say that it's a unipolar junction. So the main difference between what we will call the Shockley barrier dot and the normal pair junction dot is that the Shockley barrier dots are a unipolar dots, while the PN junctions are a bipolar diodes or a bipolar devices. So now we investigate together the first combination. What I mean by combination is to have phi m greater than phi s and to have a semiconductor which is n-type. Whenever you have two variables, then you have four combinations. So let's start together to check another combination. Our next combination is, my dear students, is as follows. Here you have now phi s is greater than phi m. The semiconductor work function is greater than the metal work function. But the material is a p-type material, not an n-type material. So you actually alternate the both conditions. In the first example, phi m was greater than phi s. Now you make phi s greater than phi m. And in the second input, which is the doping, in the first case it was an n-type. Now it becomes an p-type. So in this case, we are going to do typically the same solution. Then, in order to make this EFM and EFS horizontally aligned, you have to push this energy band diagram upward so that these two lines are aligned, like this graph. And in this case, you will push this with a distance equal to the difference between these two lines, which is phi s minus phi m, as you can see here. So phi s minus phi m is the barrier. Now this is the energy band diagram, as you can see. And let's start to ask the same question. Does the majority carrier here will be able to move to the metal side? Now the majority carrier is holes. And as you know, the energy of holes increase downward. So whenever you have holes here, these holes will face a barrier here and will not be able to move to the other side of the material. Accordingly, this phi s minus phi m is considered as a barrier with respect to the majority carrier with its holes. That's why this is another type of a Shockley barrier dot. So whenever you alternate the two conditions, you make phi s smaller, greater than phi m, and the material is a p-type instead of n-type, you will result with the same condition. Accordingly, you have here two conditions: either to put a forward voltage, which is again the polarity of this voltage, so you get rid of this barrier and return it to be drift, or you can increase this barrier by adding a reverse voltage, typically like the first example. So these are the two cases where we have a barrier Shockley dot. Now, let's turn to other examples. We have already investigated two cases. The first case, phi m was greater than phi s and the material is n-type. The second case, phi s was greater than phi m and the material was p-type. But what if this condition? As you can see here, phi m is smaller than phi s and the material is n-type. So this is typically like my decision in this case, but with phi m smaller than phi s. This is the only difference between the third case and the first case. So Again, we are going to do this typically the same solution. What we are going to do is we are going to make a horizontal Fermi level. In order to make a horizontal Fermi level, what we are going to do is to push this upward with a distance phi m minus phi s. So whenever you push this upward, you will get this shape. As you can see here, this phi m minus phi s. Or sorry, this is phi s minus phi m because phi s is a greater one. But herein you have to take care of very, very important part. Now the majority is electrons. So this is considered as a drift from the electron perspective. Whenever you have an electron here, this electron will automatically drift to the other side. That's why we call this as an atomic contact. This is the most famous semiconductor metal interface. This is the metal semiconductor interface used for every electrode. Whenever you have any device, and in order to connect the device with external voltage or whatever, you have to have what's called an electrode. I believe you already know, and maybe you already see this electrode. So what is the electrode? Electrode is a metal contact that is contacted to the semiconductor, and it used to drift current and apply voltage. So whenever you need an electrode, this electrode should be in a form of an atomic contact, not in a Shockley contact. Because in the Shockley contact, you have to apply an external force to make it drift. But in the atomic contact, you don't have to do anything. The current or the electrons will automatically collected by the electrode due to this drift. So this is the philosophy of the concept of what's called the atomic contact. So this is the atomic contact. Perfect. Of course, you can do another type of atomic contact. Again, this is a unipolar junction because herein the majority is electrons. So you are collecting mainly electrons. So you can collect hole by applying the force condition, which is simply to have phi m greater than phi s, but the material is p-time. So now this energy band again should be pulled downward with a distance phi m minus phi s, and then you have this bending here. And if you remember, the energy of the photon, sorry, the energy of the holes decrease upward, so the holes now will be automatically collected by the contact, which is the atomic contact case. So simply, you can build a unipolar electron collecting electrode or a unipolar holes collecting electrode. This simply depends on how you have or what type of semiconductor you have. So, for example, in a very easy manner, in this p-n junction, the diode you have in the lab, in order to make this diode working, you should connect two electrodes, one to the n side and one to the p side. These two electrodes are those we are going to connect your wires with. So in this here, you have a p side material. Then you have to connect a metal here. And this metal should satisfy the force condition, which means that this, in this case, phi m should be greater than phi s. And vice versa here. Phi s should be greater than phi m because this is an n-type. So again, this is a few cases. Let me highlight it again. So this is an n-type. So phi m should be smaller than phi s in order to create what's called dynamic contact. And here, phi m should be greater than phi s in order to have an atomic contact for holes. So you can collect electrodes or you can collect holes based on the type of the semiconductor material you have. And this is what's called the atomic contact. Okay, perfect. So let's do a final stage. As I mentioned in the beginning of this lecture, that our target is to study three types of contact: the atomic contact, the Shockley barrier diodes, and what's called the heterojunctions. Heterojunctions is a very wide range of devices in semiconductor semiconductor field. And of course, it's impossible to cover everything in one slide. What I'm going to show you is just a brief conceptual view to what's called the heterojunction. As I mentioned at the beginning of the lecture, heterojunction is the concept of having a semiconductor junction, but with two different materials. So whenever we build a p-n junction, like this one, for example, we are using, for example, a silicon. So it's in one side, it's a silicon p-type, and in the other side, the silicon is an n-type. And then we are merging these together. And the evidence for that is that the energy gap, which is a material property, is constant everywhere because it's the same material. But what if you combine two different materials? For example, silicon and gallium arsenide and gallium indium phosphide, or whatever, two different semiconductor materials. Then basically, these two materials will have two different energy band diagrams. Also, two different energy gaps, as you can see. This is easily observed here. Again, under thermodynamic equilibrium, you have to have the both E Fermis horizontally aligned. So whenever you start plotting this energy band diagram, you are going to start with an horizontal Fermi level and plot everything with respect to it. But the problem is in continuity. So let's see this problem. Let's try to do it together, this example. Okay, so we have something like that. This is the first material. And for example, this is a p-type, like the example we have in the lecture. So this is a Fermi level. Let's call it EF1. And this is EC. And this is EV. And we have another material with a smaller energy gap. And the Fermi level is here. Okay, so this is E Fermi and E Fermi 2, and this is EC, and this is E. And we are going to apply typically the same procedure we have already done for other junctions. So you will start with an horizontal Fermi energy band. Okay, and you will say that, okay, this is the conduction band for the second. This one is this one. And now this is a p-type, so you will have to make this like this, for example. Perfect. And you need to put this here to make this as a p-type. So this is the Fermi level. So this is EC, and this is EV. And you need to put this, for example, here. As you can see, my dear students, usually in the normal p-n junction, we have a parallel form. So this line should have a parallel line. So it should go like this. But this Fermi level, this valence band is not downward, it's here. So you will have what's called an energy band gap spike. An energy band gap spike. So the energy band gap will look like this. This spike is an output of the discontinuity in energy gaps. These two energy gaps are not equal. So you will have this spike. Of course, my plotting is too bad, so let me return to a better form in the presentation. So you will have something like this. This spike, of course, this can appear in the valence band or in the conduction band. So this spike is due to the discontinuity in the energy band gap. Here, the plotting is more consistent and into scale so that you can see it in a better way. This spike is actually very, very recognizable spike in the semiconductor field. And it is the main reason to what's called to have an internal boundary or interlayer capacitance. Usually, we agree that normal p-n junction have a capacitance due to the depletion region, but this is another source of internal capacitance. This is simply because in this region, as you know, holes energy is going, holes energy is decreasing upward. So automatically holes will be accumulated in this spark, because any hole here will automatically go there. But holes will never be able to pass this barrier. This is a very sharp barrier. Accordingly, you have holes here and you have holes there, and this is a depletion region, so this is a capacitance. We call this as an accumulation region because here you accumulate a huge amount of holes which are somehow bounded in this well and will not be able to move either to the right or to the left. So you have here a capacitance effect. And this is one of the phenomena associated to the heterojunction. Of course, this is only one example of a heterojunction. You can have different examples. Simply, you can turn the game to have the N side with a higher band gap and the P side with a lower band gap. So you will find that the spike will be turned into the conduction band, and you can make different shuffling for the inputs and get different energy band gaps. Again, as I mentioned, this is just a very brief introduction to the heterojunctions. It's, of course, more and more wider than that. It's a very big element in the semiconductor devices. We use heterojunctions in many devices across our life. So maybe you can use this information to get more whenever you face a heterojunction in your next courses or maybe in your courses or whatever. So this is the termination of this short lecture dealing with metal semiconductor interfaces and heterojunctions. Actually, the correct name for this lecture should be a metal semiconductor as well as heterojunction, because we already studied heterojunction, which is semiconductor interfaces. That's the end. In the next lecture, we are going to start a series of lecture about metal oxide semiconductor field effect transistor, which is, from my perspective, is considered as the core element in this module, how to study all perspective for these metal oxide semiconductor field effect transistor or transistor. Thank you very much for your concentration, and see you next lecture, inshallah, with the MOSFET. Thank you and bye.